Yeah, so I already also posted on Canvas the practice exams. I'll upload the solutions by the end of the week. My idea probably also by the end of the week, I'll just give you kind of like a preliminary grade in terms of like classwork, like say, how much of like probably like I think by now all of you should have like all the points in recitation slash quizzes if you kind of like just showed up. So I'll just kind of tell you this is what you have on that, this is what you have on my lab, and all the other stuff. And if you are missing some points, then I'll just tell you to finish doing certain assignments, and then you can get all of them. That's more or less how I deal with that to just make it easier for everyone. So if you, after they send the email, if you have all the points, then that means that you're kind of good to go, and you don't have to keep working on my lab or anything else. And then you can just focus on, the final exam and whatever else like you have to do in the remaining classes, of the semester. So, but yeah, I'll try to get that done around Thursday, Friday of this week. For now, what we have to talk about today is kind of like one of the next topics of the course, I feel, because it's one of the more applied ones, which is related to work and conservative forces. I'll tell you about that today. So let me start with an example. Things we have in mind. So maybe you have seen it before. You have taken like a physics class. So let's say you have like some box or some like a brick or some object, okay, and you want to move it from this location to this location, and you just move it like along a line. So like you just you give it a push, and you just like shift the position of the object. So maybe this is like the initial position. This is the final position. Okay, and to move it, let's say, okay, you have to use like the standard units in science. Like let's say like the displacement was 5 meters. So that's the net displacement. And then let's say that you apply like a force to move it, and the force that you applied was 10 newtons. Okay, and it's completely horizontal, so it's perfectly aligned with the displacement. And let's thinking like that this is like the x-axis, I'll just say that it's in the direction of the vector I to specify that it's like completely horizontal force. Okay. So there's this thing that you may have seen before, which is like the work done by this force on the object, and it's just in this case done by F. Well, in this case, ends up being like you basically multiply the two magnitudes of the force and the displacement. So it's 10 times 5, which is 50. But I'll call it W for work. And that's just, in this case, 10 newtons times 5 meters. And then this is like 50 joules. Okay. So it is supposed to be a scalar. So this is going to be a scalar or a number. Now, there is a slight variation of this problem where it's like, let's say you have the same mass, the same object. You apply this, you have the same displacement, but now the force is not, the force is not perfectly aligned with the object, but it's rather at an angle. So let's say the force, I'll think of it as being 10 newtons in magnitude, but now it makes like, what is the angle that I use here? it makes a, like, say, like an angle of 60 degrees with the displacement. Okay. So here it is parallel, like here F is parallel to the displacement. And here there is an angle between the force and the displacement. Okay. In that case, you can still talk about the work done by the force. Um, the idea is that you kind of want to take the angle into account in some way. So what you do is multiply the magnitudes like of the vector. So it's like 10 times 5. But you also multiply by the cosine of the angle between them. So the angle between these two vectors is 60 degrees. So you would multiply by the cosine of 60 degrees, which hopefully is like 1/2. So that would give you 25. Okay. And the important thing here is that if you think about it in this way, like, if you haven't seen this before, the important thing like of this like example, which is more like motivation, is that you're multiplying the magnitude of the force times the magnitude of the displacement. Let's call this displacement delta R. Times the cosine of the angle between them. But in this course, we saw a formula, right, which was like the magnitude of two vectors times the cosine of the angle between the vectors. That was precisely the dot product, right? So in this case, like this formula for the work happens to be the dot product between the vector F and the displacement, okay? Does that make sense so far, so good? No, how is it related to some of the stuff we were doing last time? So last time what I was talking about was how do you integrate like a function along a curve, right? Now we're not dealing with the function, we're dealing with a vector, right? Like the vector f. So like the generalization of these two cases is now where you have a curve, right? So imagine that now like you have like this box or like this object with this mass, and then you want to take it from here to here, right? But now you're not like moving it along a line or something like that, but rather some more complicated curve. So just imagine like you're transporting this object from this point to this point along some road on the plane. So this is like a curve. Okay, so you're moving the box along the road, and then as you move the box, you may be applying a different force throughout the way, throughout the path. So maybe let me draw some arrows, which like the important thing of like the arrows that I'm drawing is more like that they're changing from point to point. I'm not drawing, besides that, I'm not drawing them with any particular like other considerations. Like the only thing I'm trying to do is kind of draw a bunch of arrows that like, they have different sides, they have different directions. So maybe it looks like this. Okay, so it's kind of like a force that is being applied to the box or the object that changes in size and magnitude, which is kind of realistically what would happen if you're moving an object, right? Because like you rarely would apply the same force to it as you move it, right? So then you could ask, what's the work done by this force, right? Along the net displacement, right? Like along the trajectory. So you could ask what's the work along this trajectory or along this curve. Okay, and the idea basically is that you kind of do the calculus, take the calculus approach, which is just like to break the curve into a bunch of tiny pieces. Okay, so let's say that you break the curve into a bunch of not segments, but things that look like segments. Right. Um, so for example, if you focus like your attention on one of these segments, the idea is that along one of these smaller segments, you have some sort of like formula for what the work is along that mini segment. So like the work along one segment, one of these segments it's basically this, it's more or less this because one of the segments is roughly lined. Like, it's not quite a line, but like that's the point of like approximating a curve by its tangent line. So if you look close enough, there's not much of a difference between a curve and the tangent line. So the work for one of the smaller segments is just this. Okay, and then the net work, right? The total work would just be like adding up all these smaller works, right? But how do you add up something in calculus? Like you take like an integral. So the formula for the total work, or like the what's also called the net work, is just the sum of all these works. But again, it cannot be written as a sum. You have to write it as an integral. And like like custom is to change delta r into dr once you put it inside an integral. So that's how you end up with this formula that the work is kind of like the integral of the dot product of f with the displacement. Okay, and I'll tell you like I'm about to tell you like a slightly better way to which we will use to compute it, but the idea is that is more or less like the way we will think about what it means to like do the integral of a vector along a curve. So when you have a vector along a curve, like in this picture, if you wanted to integrate that vector, what you do is like integrate that vector with the displacement vector of the curve. Now, in practice, like the way we will use this is like, you know, use this a small trick, but which is very convenient, which is like kind of like the chain rule, which says that you can divide and multiply by dt, where if maybe you think that the curve is being parameterized by time. So here, let's just assume that it's parameterized. So once you like write like a point on the curve in terms of time, you can which you could think of maybe just giving you the position of the object you're moving at in terms of time. So once you do that, you can rewrite this dot product in this way. And this is nice because the derivative of the position with respect to time is just the velocity. So this is all just to say that, and this is actually like the way we will uh, deal with this problem is that to find the work, let me write it here. The work is just going to be the dot product between f and the velocity vector of the curve. Where here v is the velocity vector of the curve. And now this does look more or less very similar to what we were doing last time, because last time, if you remember, to integrate a function, what we would do was, what we did was integrating the function times the magnitude of the velocity vector. So last time, to integrate a function, we did okay, which is similar. I mean, the thing is, like, the function is already like a scalar, so uh, this more or less works for the function. But when you're dealing with a vector, if you want to produce a number, the easiest way to produce a number, if you know two vectors, is just to take their dot product. So that will be, I'll write this again, but this will be the way we will use to integrate a vector along a curve. We take the vector, take its dot product with the velocity of the curve, and then do the integral of that. Are there any questions about this? The dot product of F with V sometimes was called power, I think. So like this is just saying that work is the time integral of power. Um, and so, and this is like measuring watts, I think. So if you have heard cars, like, when they refer to the motors, like their horsepower, I think like that's like a common phrase, like that's kind of like the type of thing that they're talking about. Like the engines, like. So let me just summarize what have been saying. So uh, here are like the steps. So how to integrate a vector along a curve? So the steps are very similar to what we did last time. So step one is to parameterize a curve. Here, so the first thing you do is parameterize a curve. So that means that you write the position vector of the curve in terms of t. So you find then step two is to find the velocity vector. Then step two is find the velocity vector. Step three is to rewrite the vector f in terms of t using the parameterization of the curve. So rewrite f. Using the parameterization of the curve. And then step four is to integrate the dot product between f and b. that okay? So let me do an example, to show you what happens, here, and like a thing that occurs, which is like an interesting situation. So there's something like, important that happens for this type of problems, which I'll show you in a moment. Okay, so let's say that you have 2 points on the plane, 1, 1, and 0, 0. And again, like just assume for the moment that there's some object placed here and you want to transport it to this point 1, 1. So the way I would choose like the easiest thing to do, which is to move it along a line. So I'm going to draw this line segment connecting these 2 points. And let's say that F, suppose. So what, well, let me just finish writing the statement and I'll try to explain what I mean when I write something like this. So let's find the work done by F. Okay, so just to explain what's happening here, like, how are you supposed to think of F in this context? The idea to think about it is this formula is for a vector, right? It's for a vector because it's given in terms of ij and k. Well, there's no k component here, so that's why I'm not writing there. But this is like a formula for a vector, and it's telling you kind of the value, what this vector is at the point x comma y. So think about it kind of as a non-constant force. It's like kind of saying like this is a force that would be applied to an object that's being put in the location with coordinates x, y. So for example, let's make this more concrete. So let's say you are at the origin, right? So at the origin, x and y are both 0, right? So what this formula is saying is that at the origin, when x and y are both 0, the formula for like what f should be at this that point would be 0 times 0 comma 3. Okay, so the f that would be applied to the box or whatever you're dealing with at this point would be 0 comma 3, or as a vector, like, or maybe let me just put it like as 3j because it looks a bit nicer, just to emphasize that I'm thinking about it as a vector. But for example, at the terminal point, right, at the terminal point, what would be the force that's applied to this object? So X and Y are both one now, right? So you put X equals one, Y equals one here, so you get 1, 3, right? Or I plus 3J. So I plus 3J would look maybe something like this. And like if you take another random point, like let's take something like 1/2, 1/2. So here you have 1/2, comma 1/2, right? And so what would be the force that's applied to this object at that point? So X and Y are both now 1/2, right? So you do 1/2 times 1/2 gives you 1/4. So that gives you 1/4, comma 3. So in this case, the force, like it has a smaller vertical component, horizontal component. So maybe so my point is that the way you should think about this formula is kind of like a recipe that tells you the force that would be applied to the object or like the vector that's being applied on the curve at a particular point there. Is that making sense? So it is not constant, right? It changes from, here is something, here's completely vertical, here's like tilted and like the angle, like the magnitude is changing and other things. So it's like a non-constant force. And that you can do for any other values of X and Y, and for any value of X and Y, you get a vector. So it's actually, maybe just to show that to you on the computer screen, it is like one of like the things that I had called before, like a vector field, right? So it would be useful to show you how that looks here. Uh, Here, let's use this one because I really like it. So the way to think about this is that this is showing you a vector and how like the components of that vector at a point x comma y. So what I'm saying is that for the one I wrote there on the board is x, y, that's the first component of the vector. So let me just enter here x times y, and then the vertical component was 3. Okay, so let me see if I can make it a bit bigger, like the, no, okay, this is too big. I don't want something that. So I don't know if you can see if you notice the how the components, like the vertical components of any of these vectors is the same size, because the vertical component of the vector is always 3. So all of them have the same vertical size. The only thing that's being changed is like how large they are horizontally, right? So like along when, like for example, the origin, what I told you is that the vector is completely vertical, and if you move, if you could zoom to, let's say from 0, 0 to what, like 3, 3, you see that somehow like the vector stretches out in the horizontal direction, right? So the important thing here is that it is not like a constant vector, and that's why it's called like a vector field. But the way you should think about it is like if I place like an object at this point, that is the force that would be applied to the object there. Is that making sense? Um, yeah.
Are most of the, I guess, forces we're working with going to be non-conservative?
For these problems, for now, it will be kind of half and half, but I'll define it in a second what that means. But yeah, like, both cases are important for us. This one will be not conservative, as you'll see in a second, which is what I'm going to use it for to illustrate it as. But um, just was trying to clarify what I mean by like F in this context, which is kind of like, I mean, you can think about it in terms of a force if you prefer. I think that's easier, but if not, you just think about it as, oh, we're going to draw vectors on the plane according to some recipe, and the recipe is like the formula is this. Okay, so sometimes like in these problems, like understanding what's going on is harder than just like actually doing the computation. You'll see that doing the computation is relatively straightforward, but knowing what that means is what takes a little bit of work in going technique. So um let's just follow the steps. So the first step for solving this problem, the first step is to parameterize a curve. Okay, so we have to parameterize the line segment. So let's call P and Q the initial and final points of the segment. So let's try to parameterize. Again, what does it mean to parameterize a line segment? It means that you have to write the position vector in terms of t. If you remember the beginning of the course, we discussed the parametric equations of a line and also like the vector equation of a line. The vector equation was that the position of a point on the line at time t is the initial position, right? Plus t times the direction of the line, right? What can you take as the direction of the line? You can just take it to be the vector PQ, right? That goes from P to Q. So that would be the vector equation of the line. Let me get some rings a bell, sound familiar. So what's the initial point? Is 0, 0 in this case. T times q, the vector PQ, which remember is Q minus P. So it's 1, 1 minus 0, 0. So you end up noticing that like the position at time t is just P comma T. Meaning, so if you prefer to write it as parametric equations, it's like that x of t equals t and y of t equals t. So like either works well for what we're about to do, although it is easier to keep it as a vector because that way when we take derivatives and things like that, we just get something simpler to work. So that is the parameterization of the line. Any questions about that? And once you have the parameterization, you can find the velocity vector. That's easy. Just take the derivative with respect to t. So that's step 2. What's step 3? Step 3 is to rewrite the function. Oh, it's not the function, sorry, the vector f in terms of t, right? So again, this is a formula for f at any point on the plane x comma y. So along the line segment, x happens to be t and y happens to be t. So along the line, you just get t squared comma 3. So that is like how the vector f looks along the line segment in terms of time or in terms of t. Okay, so making sense. And now it's more or less ready to go because you take what you have to integrate is the dot product between the velocity vector and f. So we have to do f dot v dt, which is t squared 3 comma, dot v, which is 1 comma 1 dt. So you can do the you should do the dot product before integrating. There's no way other ways to do this. You are going to integrate t squared plus 3 dt. And you do need to give bounds to this integral. So what are the bounds for t? Well, it goes from the initial time to the final time. At time zero is where we are located at the origin. You can just look at it from the parameterization. And time one is when we are at point Q. That's easy to see. So the bounds for t goes from 0 to 1. So you just get t cubed over 3 plus 3t at 0, 1, and that gives you 1/3 plus 3, that's 10/3. Is that what you said? Okay, so this is a particular example, like what the work would look like if you thought about F as being a force and that particular choice. Now, what's interesting in these problems, and you'll see why that is interesting in a bit. Is that there are other ways for going from point P to point Q. Oh yeah. So you have to think about what value of t do I have to put log in the parameterization to get the origin, which is the initial point, and what value of t do I need to plug in to get q, which is the final point. So since the initial point is 0, 0, you get that 0, 0 has to be equal to t comma t, and that's how you get t equals 0. And q, which is a final point, is similar to these problems when we had like the curve. You have to find the time at which the curve passes through the point. And so for q, which is 1, 1, you just equate 1, 1 with dt, and that's how that works. Happens, yeah. Um, so in this problem, like the only going through like a line segment is not the only way for going from point 0, 0 to point 1, 1. So another thing you could have done is to choose another curve. So let's do that. So and instead of moving along a line, I'm going to move now along a parabola. So let's say you have the parabola here, y equals x squared. Okay. So now I want to find the work. So find the work done by the same force, find work done by F. So this is the same F as before. But now the curve chosen, but now the curve from point from P to Q. is the parabola y equals x squared. So basically, I'm keeping the same f, I'm keeping the same formula for f. I'm keeping the same endpoints, like the same initial point, the same final point. The only thing that I'm changing is kind of like the trajectory or the path that I'm choosing to connect the endpoints. Okay. So how do you find the work in this case? You do the same. So you parameterize the curve. So what does it mean to parameterize the curve in this case? Parameterizing the curve again means to write everything in terms of a single variable t, right? So if you are along the parabola, because when you're along the parabola, you can say that y equals x squared, right? So this can be replaced as x comma x squared. And so along the parabola, everything depends, at any point is really determined by x. And then the usual convention is just to replace x with t, just so that we keep using the same variable for everything. So the parameterization of the parabola is just t comma t squared. Okay. That makes sense. No, I did that. So it's really just taking the equation of the curve and relabeling x as t, basically.
Wait, if f is equal to t, shouldn't it be t squared t?
So the thing is, like, the parabola is y equals x squared, right?
Yeah,
So the second coordinate is the x squared, right?
yeah.
So so everything depends on x here, right? I'm just saying to relabel or call x t. And so like the second entry is the one that becomes t squared. Is that making sense? Because like, I mean, if I'm like, just think about it in terms of the equation. I'm saying like y equals x squared, right? But if I'm telling you now that to call x t, then this is the same as saying that y equals t squared, right? Is that better?
I think we got it.
Yeah, and then this would be the parameterization. Once you have the parameterization in terms of the curve, then more or less everything else works in a similar way. So once this is the parameterization, step 2 is to find the velocity vector for this curve, which is 1 comma 2t. That's step 2, and step 3 is to rewrite the f, not the function, the vector f in terms of t. But what does it mean? Now it's x on the parabola. X on the parabola is t, but y on the parabola is t squared. So the first entry is x times y, which becomes t times t squared. So that gives you t cubed comma 3. Okay. Is that making sense? Is that okay? And then the work is the dot product between f and the velocity vector. In this case, like t also goes from 0 to 1 because those are the values for x along the parabola, connecting these 2 points. So this is also like an integral from 0 to 1. So that just gives you t to the 4/4 plus 3t², 0, 1, and then, right, and what is that? That's a quarter plus 3. That's what, 13, that's 13/3. Oh, 13/4, right, thanks, yeah. Perfect. The number itself doesn't matter too much, except for the fact that it doesn't give you the same as before, right? So that is kind of like the important thing to emphasize for this type of problems, which is an entirely natural thing to expect if you have never seen this before, which is that even if you have the same formula for f, like even if you have the same formula for f, the answer for the work, what the work ends up being depends not only on f and the endpoints, but also on the particular trajectory connecting the endpoints. So the way this is usually said is like work is path dependent, or like is trajectory dependent. So let me write that down here. Like actually, I should do the picture again. So, but then I'll write what I want to say. So what I'm trying to say is that if you choose to, if you choose a line segment path, the work was 10/3, right? But if you choose the parabolic path, right? The work along the parabola was 13/4 quarters, right? So even though they share the endpoints, right? They, for the same f, they do not give you the same answers. So the work done by f depends on the actual trajectory chosen, or the actual curve chosen, not just the initial and final points of the curve. On the actual curve chosen, not just the initial and final points. Is that making sense? Uh, what will happen next Monday, I think by then I can tell you that. What's really cool, and it's one of the three main theorems of the course, like or of all of calculus, it's called Green's theorem, which is that the difference in work, right, like the net difference, the difference, like in having, like, taking the difference in the work along the curve, along the line segment versus the difference in the work along the parabola can actually be computed in terms of a double integral of the region enclosed between the curves. So if you see, these two curves kind of close up because they share the endpoints. So there's like a double region here, and there's something you can integrate in this double region that will give you the network, which is how you would call this. And that's kind of one of the most important things, and that's called Green's theorem. And I'll tell you, I'm sure like by Monday, I will be able to tell you what you have to integrate. So that is kind of like one of the biggest goals of the course, just to be able to explain what Green's theorem is, which then generalizes into Stokes and the divergence theorem. But they're basically just versions of that for like in 3 dimensions. Okay. But so my point is that in general, if you don't know anything about f, so if you don't know anything about f, like the safest bet to make is that the work depends on the trajectory chosen. What's really what's really interesting is that there are some forces for which something better happens. And what happens is that like the work actually only depends on the endpoints. And that's like a very special circumstance, like not something that you would necessarily would have expected anyways. And so these are called conservative forces. So a force is conservative. There are different definitions, but it's kind of like the route that I'm taking to explain it to you. There are different characterizations of this. Um, so, but there are forces or there are vectors F, there are vectors F, or parentheses forces because that's how I'm thinking about these things. For which the work only depends on the endpoints and not the curve connecting them, for which the work done by F only depends on the initial and the final point and not the particular curve that connects those 2 points. Only depends. On final points. And not the curve chosen, and not the curve that connects them. And not the curve connecting these 2 points. And such a F is called conservative. Okay, such an F is called a conservative force or conservative vector. Such an F is called a conservative vector. So just to like emphasize what I'm trying to say, so the idea is that the idea is like if you have a conservative vector or conservative force, what occurs is that you take your two favorite points in space. Okay. And there are multiple ways to connect them. So one way to connect them is to draw something like the straight line, right? So let's call this curve one, right? And let's like I'll put some arrows just to indicate that I'm moving from point P to Q. That's kind of useful. So then but someone could say, no, I want to take like a more interesting curve trajectory. So maybe someone wants to move like kind of like this. So this is let's think about it as curve two. And then someone could think want to do something even like crazier, and then like you just are like, okay, I want to do something like this. Okay, now you do something very chaotic, right? To get from point P to Q. And that would be curve three, right? If the force that you choose, if the force that what you was used is conservative, the work along the first curve will be the same as the work along the second curve, which will be the same as work as along the third curve, which will be the same as the work about along any other curve you could possibly draw on, like that you care about. So if f is conservative, if f is a conservative force, um, the work along the curve one is the same as the work along the curve two, which is the same as the work along the curve three, et cetera, et cetera, et cetera, for any other curves you could ever draw, like basically. Et cetera, for any, same work for all curves. Same work for all curves connecting P and Q. I am assuming that P and Q are kind of fixed, but you can like, then, that making sense? And that like, again, maybe if you haven't seen this before, like, which is more likely, like, okay, this may or may not sound important, but it's actually like a very important property, like, and it's very useful to determine ahead of time if something is conservative or not. Like, you do want to have like some sort of like, toolkit to, that would give you, okay, like you do a test on the vector that will come positive, like, like true or false, like, are you conservative? So, first, like, here's a useful thing to think about. So let's say that this is actually in practice how you could check for this. What if the curve, let's say you choose like your favorite point in space, and the curve that you choose is what you would call like a closed loop. So it returns to where you started, like kind of like a circle, right? Or an ellipse. So my claim is that just with what I told you, you can already tell me the answer for what the work should be along a closed curve. So if f is conservative, let's say you have like a conservative force. So let me draw some arrows here. Let's say that f is conservative. Suppose f is conservative. F is conservative. And C is a closed curve. So what do you think the work of f should be along C?
Zero,
Yes, so like,
because you're going back to where you were originally.
yes, like, would you go to say zero also, like, or?
Yeah, it's zero, and you, I don't know, you can sort of tell because a spot has to have the same value no matter if you take it at the end or the beginning.
What do you?
If you draw a curve, if you made over a curve of length zero, obviously that's gonna be zero. That's gonna have, and since they both have the same endpoints, starting point, then your other curve is gonna be zero.
Okay, that's like a very clever argument, but like, I don't want to think of, I mean, I don't want to abuse, I mean, because, right, if you say like, or something is something of a length zero, a curve, yes and no, right, like, it is, yes, but I do want something a little bit more like, with less work with curves of actual length, yeah.
You split up into two curves.
Right.
And have them have the same endpoint.
Correct.
Because they have the same beginning and end point, the work will be the same, and so.
Perfect. Yes, like that's actually like the preferred one. So let me draw like the curve as some sort of like circle just to make it easier. So. So like, just imagine that, let's think of the closed curve as two curves. So like what I have been saying is that if you go from P to Q along the first curve, which I'll put in yellow just to kind of distinguish them. And then this keeps happening because I don't know why. So let's call this curve one. Right, and let's say that this is curve two. Right? So curve one and curve two are going from P to Q. And if F is conservative, then their works must be the same, right? So if F is conservative, the work along curve one is the same as the work along curve two. Does that make sense? But to get the closed curve, what we're going to do is kind of like travel along curve two in reverse, right? So what is like the actual situation here? Let me, I think we can draw it. So for the curve that we care about, the curve like, or like the original curve, like one way to think about the original curve is that, like, think about it like as a literal road that you're driving along. So you can drive from P to Q using the same direction as the yellow curve. That's why the arrows are kind of important in this type of problems. But then you drive from Q to P, so you're going against the green curve. So I'll put like the arrows going backwards, right? So the work along the total curve, right? Like this work here makes sense to, and it will be correct. It is the work along the first curve minus the work along the second curve, because now you're going backwards. If you're going backwards in reverse, then the velocity vector changes its direction, like turns like a 180-degree like change. And so the dot product changes sign. So the work here is like the work along the first curve minus the work along the second curve. But we already said that they have to be the same, so that's zero, right? Isn't that kind of clever? Actually, it's like a very cheap proof. And what it tells you in practice is that if you find a single curve in the universe where a single closed curve in the universe where the work is not zero, that means that that force cannot be conservative. That's kind of like the way you should think about it. So let me write it down in works. So like, consequence of this is that you just need one single curve that works like this. If you find just one curve, at least one curve, like you don't need to find a million, like you just need one. So if you find a single curve in the entire universe, so a single curve, oh, in the universe, but let's put it like a single closed curve, sorry. Where the work of F is not zero, then that F could not be conservative because of what we just did. Where the work of F not zero is along this curve. Then F can't possibly be conservative. Okay. Does that make sense? And here's like a cool application of that, and I'll finish here, and then next time I'll tell you how do we detect whether F is conservative or not. So if you have like here's like a cute application of this. So like imagine that you have like a wire and there's some electric current passing through it. So like you have like a wire and there's some current passing through the wire, which usually is could be used I like. Then there's one of these laws, I think the Biot-Savart law, or one of those, which tells you that a flow of electric charge produces a magnetic field. And the magnetic field for like a wire in this setup is just kind of like like in circles, like kind of like this. It's like how should I say it? So like the magnetic field that a wire produces is not like parallel to the direction of the current. It's more like, you know, it spins along the current. So like I'm not sure why I'm missing that phrase. So it's kind of circular, for lack of a better word, because I'm not sure why I forgot to say this. So so there's like in fact, it's kind of like a fun thing to do. If you buy like these magnetic fields, you can play a little bit with this. Like just put like turn on like like your favorite electronic gadget in your house, pass a current through it, put some feelings on the floor, and you'll see like the magnetic fields like. I'll bring it next time, like if you want to, like, and then you'll see like that. You can literally see the magnetic field. And then I think one of the important laws of magnetism is, I think it's like the Biot-Savart law that says that if you have like a curve like this, right? If you choose like the curve, for example, like to be like a circle, but it doesn't have to be like that. That is well, like it's a constant times the electric current of the wire. This is all that you need. Like if you take the curve to be a circle, this is non-zero. And so that tells you that a magnetic field is not conservative, more or less. So that's a proof, like that's the end. Like you know that a magnetic field cannot be conservative. It's actually related to the fact that the field lines can be closed, and it's actually related to the second exam problem about moving through orthogonal surfaces, but I'll tell you how that's related there. But in general, this would be non-zero. And so that means that B cannot be conservative. And so a magnetic field is not conservative in general. An electric field is under certain assumptions. So B is not conservative. Yeah. But it's very elegant. You don't know anything, not know much about what B is. And now you just told me like it's not conservative. And so that is like that is like in a sense how you actually end up using these tools. Like it's like a very, very powerful argument because it's just saying you only need like a single curve in the universe where this happens and then it's done. Like it cannot be conservative. Okay, so let's finish here and next time I'll tell you how do we detect if a vector field is conservative or not. So I'll tell you that on Wednesday.